All right, we are in Unit 2. We're just doing some practice problems and review for the Unit 2 exam. And in the last problem, the reason why I'm backing up here is in Part D, I felt like I kind of moved fast from that, and I got some questions on this video on what did I mean by this. And it said, what would you predict about a student whose Friday score was 1 standard deviation below average? Well, the point is, if you remember, it's correlation times the standard deviation. So it's R times S will help you find the standard deviation of the new thing. And the point is 1 standard deviation below here. Remember, it's R times that. Well, the R we knew was 0.473 because it was given to us in Part A, or we found it, I should say. It was the correlation. When we put it in our list, that was R. So times 1 would be our standard deviation. So that's why it says a student with a Friday score that is 1 standard deviation below the mean, they're expected to have a Monday score that is also 0.473 standard deviations below the mean. Well, that's why then we said, okay, so if I take all the Monday scores and find the mean and standard deviation of that, which I did, right? So the student's score, what would the student's score be predicted to be? Well, if it's that, that's what the mean is. That's how many standard deviations away, but it's predicted because we have to use the R now from what we had before, and since it's a decrease, that's why it's minus that, because it says standard deviation below, so that times what we just found the standard deviation to be in correlation with that, so that's why it's another R times S for that, so that's why you're taking that away as what the predicted value would be. That R times S is like a predicted way of figuring it out, just something to remember. And then we did all those, which I think were fine. But anyway, colorblindness. Although some women are colorblind, this condition is found primarily in men. Why is it wrong to say that there's a strong correlation between sex and colorblindness? Well, first of all, correlation is a strong word. It says gender and colorblindness, they're both categories, right? So correlation is a measure of the strength of a linear relationship of quantitative variables, so that's why that's not really possible. And the proper terminology anyway would be an association, or it's associated with it would be the proper way. All right, so you can't use that word, especially if it's not even quantitative. All right, here it says it's commonly believed that people use tips to reward good service, and a researcher for the hospitality industry examined tips and ratings of service quality from 2,645 dining parties at 21 different restaurants. The correlation between ratings of service and tip percentages was 0.11. Describe the relationship between quality of service and tip size. So, point is, if you're seeing that a correlation without any data, without me doing anything, or I see the correlation is 0.11, it's positive, right? But it's pretty weak if it's close to 0. I guess it's linear, right? Because it says for hospitality, right, there's 21 different restaurants, the correlation that they're giving us, so that's all that I know. I'm going to say that it's positive. I'm going to say that it's linear because I don't really know much else. But it's not very strong. It's definitely going to be weak, right? Between tip size and rating of service. And generally, better tips are associated with a better rating, but the relationship is so weak that it may simply just be due to some kind of error that happened. But find and interpret the value of R squared. Well, R squared is 1.21, so we'd say only about 1.21% of the variability in the tip size, because that was the Y, is explained by the variability in the rating service, which was X. In September 98, the issue of American Psychologist published an article that reported on an experiment, right? And it said the social and psychological impact of the internet of 169 people in 73 households during their first 1 to 2 years online. In the experiment, 73 households were offered free internet access for 1 or 2 years in return for allowing their time and activity online to be tracked. The members of the household who participated in the study were also given a battery of tests at the beginning and again at the end of the study. The conclusion of the study made news headlines. Those who spent more time online tended to be more depressed at the end of the experiment. Although the paper reports at more complex models, the basic result can be summarized in the following regression. So here's what they came up with, right? R squared was only 4.6%. All right. So, the news report about this study clearly concluded that using the internet causes depression. Discuss whether such a conclusion can be drawn from this regression, and if so, discuss the supporting evidence. If not, say why not. So, here is what we have, right? We can set up the equation for it, but only 4.6% of the y-axis variability is associated with x-axis variability, which I believe the y-axis was depression. So only 4.6% of the variability in depression can be associated with the variability in internet use. Doesn't seem too high to me. So first of all, no association between variables can be implied by cause and effect relationships. So my point is, when we're looking at this, we're looking at depression and we're looking at internet, and it's hard to put numbers associated to all of them. So what they're implying here is variables, the cause and effect relationship. It's not too likely to just say point blank, because that's what it was implying, right? Internet causes depression. No, point blank. That's hard to say. So the point is, you can't just say that it's a cause and effect relationship. Therefore, there's probably lurking variables that explain the increase in both internet use and depression. And additionally, provided the association is linear. If this is a linear relationship, only 4.6% of the variability in depression can be explained by that. So this is very weak in terms of what it would be. Taking a look at this one, consider the association between a student's scores on a French vocabulary test and the weight of the student. What direction and strength of correlation would you expect in each of the following situations? All right. A French vocab, you're probably learning French the older you get. I can't imagine being young, right? If you're around here, I don't know. And you probably know more vocabulary the older you get. I'm assuming the older you get, the larger you get. So I'm assuming the farther out you go, the higher it is, would be my assumption. So it says most of the students would have a similar weight, regardless of their individual French vocabulary. So the correlation between them is probably nothing, meaning you could assume that the higher up you get, the older you get, but it says the students are all in third grade. The students are in third through 12th grades. So part A, it says if the students are all in third grade, their weights are all the same-ish, right? And the amount of vocab they know should be pretty close as well. So there's probably a whole bunch of dots of points where it's all probably around the same thing is what they're saying, which is why most of the students probably have similar weights, and regardless of their individual French vocabularies, their correlation would probably be near zero with them, right? There's not going to be much variability with them. However, the students are in 3rd through 12th grades in the same school district. This school offers, depending on when the school offers French, but the correlation would probably be positive and strong because older students would typically weigh more and they would have a higher score on their tests, because the higher up they get, you would assume the smarter they are because they keep getting up. So if French is not offered, the correlation between weight and test score would also be near zero because they might not even offer that many French classes. The students are all in 10th grade and in France. Now, for that one, they're all in 10th grade, but they're all in France. So they're all in the same grade. So they should all know about the same stuff, right? So they should all be in the same area of knowledge as it goes, which means it should probably be a pretty straight line. Even though they are in France, most of the students would have similar weight and they'd have similar vocab. But the students are in 3rd grade through 12th grade in France. Again, you would expect positive and strong because the higher up they get, the more that they know. Is basically what you would be expecting. Find and predict the values of y. We did some of these. You plug in a 10, straight up you're good. You plug in a 10 here, but remember to get rid of that. You do. There is no number with logs, so that's a 10, so it'd be 10 to the 2.7. Here again, when we're doing this, as you plug in 10, I end up getting a number over here, but I would multiply by root y, then divide by that new number, and then I'd square both sides, so technically it should be a squared there and there as well. Here it says, how are companies' profits related to its sales? Let's examine data from 71 large U.S. corporations. All amounts are in millions of dollars. So a histogram is made, right, of profits and sales, and histograms of the logarithms of them. Right, so I'm looking at this, I'm not really seeing much, right, profits and sales. But then I decide to log the profits and sales to see if it helps with the logs when I'm graphing them to see a difference. And it says, why are the re-expressed data better? Because now I can see more with them. I can see more of a symmetrical shape with them as well to make it helpful, right? I see more symmetry, which means very few outliers, if any. That's good for regression because there's less of a chance for any kind of influential points, right? Additionally, symmetric distributions of explanatory and response will help ensure that the residuals around the line through the data are more unimodal and symmetric, and we will learn more about why this is important later. For the time being, symmetric data is more helpful when we are talking about stuff. And here are the scatter plots of the residual plots for the regressions of the log, right? And then that is the predicted one, so it kind of is looking positive when I log them both. I'm not seeing much of a pattern, so do you think this model is appropriate? Looking at it, I think that there is a linear positive and strong association, and the residual plot shows no pattern, so I'm thinking it's pretty good, right? I'm thinking it's a pretty good use of it. I'd have to look at the R squared to see if one's better than the other, but the point is it's looking like a good model to me. Then it says here is the regression analysis for the equation, right? And it says use your equation to estimate profits earned by a company with 2.5 billion. Well, the linear model right here is given, log of sales. So the point is when you plug this in so we can get some practice, it says plug in $2.5 million, right? So when we're doing this, I plugged in because it's in terms of thousands, so that means 25 million. So I plugged that in instead because that's what it asked for. So I plugged in the number that it said. I got this, but remember to get rid of that, it's 10 to get rid of that. So it's to the 10, I get 124.43. Is roughly what I get for D, and it says according to the model, a company with sales of about $2.5 billion is expected to have profits of nearly $124.43 million. And again, I hope that was a big help, right? I hope this was a pretty big help to kind of get us through Unit 2 with some good reviews. But again, I hope you were following along and look through a lot of the practice problems in each of the sections. That'll help you out with the unit test even more if you kind of go back through more than just the review that we just did on top of everything else. All right.